Okay. We were studying inner product and okay, and it was a theorem that says for a non-empty closed convex subset of a Hilbert space, H, I think I told this, so let's pass this theorem. And the remark, I remember that I spoke about the remark. Okay. Orthocondesis, okay, we studied this section 2. Okay, maybe, oh, okay. I studied all these sections. Okay, now we are here. Remark. The linear span SPEN of the set En consists of all possible finite linear combinations of the vectors in En. Okay, we know the span of En is this subspace of X consisting of all vectors that are the finite combination of En. So for any x in H, it is necessary to also consider infinite sum. If we have infinite sum like 3.5, this considering the closure of SPN. So when we speak about the closure of SPEN, we may have infinite combination of sums, combination of En as an infinite sum, and for SPEN we consider finite linear combination of the vectors in En. Now we have this definition. Let H be a Hilbert space and En be an orthonormal sequence in H, then En is called an orthonormal basis for H if and only if the conditions in the theorem holds. We know that in this theorem as you see, when H is a Hilbert space and En is an orthonormal sequence in H, then the following conditions are equivalent. So if we have any of these conditions, we have the others. For example, if we have A, the orthogonal of this set, all En for n in M equals the singleton 0, we have the other conditions. These conditions are equivalent. So if we have one of these conditions, we say that this set is orthonormal basis, not just orthonormal sequence. So as you see, let H be a Hilbert space and En be an orthonormal sequence in H, then En is called orthonormal basis for H if and only if any of the conditions in theorem hold. Remark: in some books, orthonormal basis is called a complete orthonormal sequence. So we can say complete orthonormal sequence or orthonormal basis. They are the same. Here the complete means there must be as much En, so they can consist of H. So we say complete in the sense that there are enough vectors. There are so much vectors or enough vectors in the H in this sequence to span the space. It means that they construct H, or the span of En equals H. Okay. For example, the orthonormal sequence En bar, En eyebrow or bar in L2, small l power 2, given the previous example, example 3.35, is an orthonormal basis that is called a standard orthonormal basis for L power 2. So for any x as a sequence xn in L2, we have these equations. The norm of x power 2 equals the sequence, the series of the absolute value of xn power 2, n from 1 to infinity, and this is equal to the sigma of the absolute value of the inner product x and en power 2, n from 1 to infinity. Another theorem: finite dimensional norm vector space are separable. Before that, we should define separable Hilbert space. What is the meaning of separable? When we say that a Hilbert space which are two lines to be spanned by the countable collection of vectors in a sequence. This separable Hilbert space. Let H be a Hilbert space H, let H let H be a Hilbert space. Be a Hilbert space. Space. Okay, if there is, if there exists or there is a countable density as a subset of H, and D is countable and dense. And dense in H I mean D bar, the closure of D equals H, and D is countable. It's not uncountable, it's countable. So H is called separable. H is called separator. So if H is called separator, separator. Okay, here is the a very common method of constructing countable dense sets is to take a general elements of a space. Okay, so it's called separator. Separator. Okay, so for H to be separable, as you see, separate, it must have a dense countable subset. Now we want to speak about separable Hilbert space by having a countable basis. Theorem: finite dimensional norm vector space are separable. So if a normal space or Hilbert space is finite dimensional, it is separable. An infinite dimensional Hilbert space H is separable if and only if it has an orthonormal basis. Orthonormal basis, you know, is a countable sequence En such that the span of En equals H. So we have this theorem. For finite dimensional, any finite dimensional normal space is separable without any further or more conditions. But for Hilbert space, for infinite Hilbert space, H is separable if and only if it has an orthonormal basis. For example, the Hilbert space L power 2 is separable because L2 has a orthonormal basis. You see the sequence Exn En bar. So L power 2 small L power 2 is separate. Let me see if there is everything is okay. Okay. We have some exercises. I will send the answer of some selected exercises to you. Fourier series, we don't need it. You can omit this. Omitted or محذوف. L2 L2 of 0 and P is separable. We don't need them. Linear operators. Linear operators are key roles in functional analysis, and they are very important. First, continuous linear transformation. Transformation is a linear operator or linear function from a vector space X to another vector space Y, such that these two vector spaces are on one field. The scalar field of X and Y must be the same. Even though X and Y can be different, but the scalar field must be the same. So we fix two normal spaces X and Y and look at the space of all continuous linear transformation from X to Y. If X and Y equals are the same, or if Y equals X and okay, let's started from this definition. We should wait because the internet now is very weak and we can't continue. We should wait until the internet become stronger, the net becoming stronger, so we can continue. Okay, now we can continue. Let's start from this situation when x and y are normal spaces and t is a function from x to y. Okay. Everything is okay? Oh. Okay, let's t be a function from x to y when x and y are two normal spaces. So we have x, y, two normal spaces, and f as a scalar field, and t is from x to y. We say that t is linear or linear transformation when for alpha in f, I mean scalar alpha, and two members, two vectors x and y, x1 and x2, we have t of alpha x1 plus x2 equals alpha t of x1 plus t of x2. We call this linear transformation. Now we have this lemma: let x and y be non-linear spaces and t be a linear transformation. The following conditions are equivalent. T is uniformly continuous. T is continuous. T is continuous at 0. There exists a positive real numbers k such that the norm of t of x is less than or equal k. Whenever x is in x and the norm of x is less than or equal 1. E. There exists a positive real numbers k such that the norm of tx is less than or equal to the k of k dot norm of x for all x. These conditions are the same or are equivalent, so t is continuous if and only if t is uniformly continuous, or t is continuous in on all x if and only if t is continuous just as one element, 0, for example. And t is continuous if and only if there is a positive real number k such that the norm of tx is less than or equal to tk whenever x is a member of x with the norm less than or equal 1, or there exists a positive real number k such that we have this inequality for all x in x. At first, this lemma says that all these 5 conditions are the same. So we say that t is continuous if and only if t has one of these or t holds in any of these conditions. This is an example, t from cf01 to f such that the t of f equals f of 0. Another lemma, if Cn in L infinity, means this is a sequence in L infinity, and Xn is in Lp. For p from 1 to infinity, then Cn Xn will be in L power p, and we have this inequality. Another example, let Cn be in L infinity, the linear transformation t from L1 to f defined by t of xn equals the series Cn xn, and from 1 to infinity. Here the norm of Cn, norm infinity of Cn equals the supremum of the absolute value of Cn for all n greater than or equal to 2. And the series of the absolute value of xn, n from 1 to infinity, equals the norm 1 of the sequence xn. Another example, let Cn be an element in L infinity, then the linear transformation t from L2 to L2 defined by t of sequence xn equals the sequence Cn xn. This is a linear transformation from L2 to itself. Definition, if f, for example, from R to R is defined such that the f of x equals, for example, sinus of x. So because we know that sinus is sin sub x is between -1 to 1, or the absolute value of sin sub x is less than or equal 1. So we say that f is bounded. This is bounded, but f of x equals x is not bounded. But when we say that a linear transformation is bounded, it means that there exists a positive number case such that we have this inequality. The norm of Px is less than or equal to k of the norm of x for all x. So being bounded for a linear transformation is different from being bounded for example, such a function. Here, f of x equals x as a real function is not bounded, but as a linear transformation, it is bounded. So, as you see, t of x equals x, t is bounded in the sense of this definition, in the sense of linear transformation, but it's not bounded in the usual sense of bounded functions, as for example, like sin of x. Notation: let x and y be non-linear spaces. The set of all continuous. Continuous, we can, as you see, being continuous in this theorem, the previous theorem, here we have 5 conditions that are equivalent. T is bounded if and only if, for example, T is uniformly continuous, T is continuous if and only T is uniformly continuous, and if and only if there exists a positive real number case such that we have this inequality. Now, in this definition, we say that T is bounded if there exists a positive real number case such that we have this. So, by the previous theorem, this condition is equivalent to the condition that T is continuous. So, for a linear transformation, T being continuous and bounded are the same. So, we say that as by the previous lemma, I told the theorem, but sorry, it was a lemma. By the previous lemma, the words continuous and bounded interchangeably for linear transformation. So we can say that the transformation is continuous if and only if it is bounded. So if x and y, let x and y be linear spaces, the set of all continuous or bounded transformations from x to y is denoted by b of x and y. Why we call this, we show this by b? The first letter of the word continuous is C. So maybe we show that by C of x and y. But we show it or denoted it by B of x and y because B is the first letter of bounded, and because the continuous linear transformation are the same as bounded linear transformation, we can show continuous linear transformation by B of x and y. So we can call this linear transformation or bounded linear transformation by the B of x and y. As you see, bounded linear operators. But if the x and y are non-linear spaces, then L of x and y, L of x and y is the set of all linear transformation, not continuous linear transformation, just linear transformation. So the continuous linear transformation is a subspace of the linear transformation of x from x to y. So we have this relation between B of x and y and L of x and y. We should wait until until internet become stronger. Now it is very weak, and I can continue. I want to ask you something. Maybe you hear the voice of azan. In Iran now is the time of azan. So I want to ask you to start the lecture half hour sooner than 4 o'clock Iraq time. 3:30. If it is possible for you, I will ask you through WhatsApp. If it is okay, start the lecture half an hour sooner. For example, 3:30 p.m. Arab time. So I will ask you and please answer me in WhatsApp if it is okay for you to start lecture half an hour sooner. Okay. So you agree with my suggestion to start a lecture half an hour sooner? Okay? So Tuesday this week we will another lecture, and we can start it 3 and half past 3 p.m. I mean half an hour sooner than 4 o'clock. Okay? I think this is enough for today. And now this is the time of Azan. And I finished the class, and next time we will start it sooner, half an hour soon. Okay. So until this exam. Okay. Any question? Somebody wanted to speak. I couldn't okay his microphone. If anybody wants to speak, please ask for microphone. So I will open his or her microphone, and he or she can speak. Nobody wants to speak? Okay. Any question? Okay. So goodbye for now, and we will have another lecture this week at Tuesday, and maybe we start little sooner. Thank you too, and goodbye.